Hello everyone, welcome to our video today on color basics. Now before we get into color, we should probably discuss first, how do we see? Seems kind of silly, you've been seeing things since the day you were born, and it's not actually the simplest thing, believe it or not. So light comes from a light source, usually the sun, maybe a lamp in your room, maybe your the fan, any kind of light source. Light comes out, bounces off an object, and then it reflects into our eyes. Now that's the super simplified version. We're going to get into the specifics of how you see different colors later on in this video. Now just to remind you, we cannot see the entire spectrum of light, right? Remember the electromagnetic spectrum? There's actually a very significant portion that we cannot see. The actual amount that we can see is very, very small. And we call this the visible spectrum. Now, again, this is not necessarily only the visible spectrum for basically everyone. There are actually animals that can see on either side of the electromagnetic spectrum, just depending on what they have developed for usually hunting purposes is a big thing, or marking, but things like bees can actually use and see UV light. And then, yeah, so it's not necessarily just the human, or this is not the all-encompassing visual spectrum. This is not the visual spectrum for everything out there, but it is for humans. Okay. Also, the specific color is determined by the wavelength. We've talked about wavelengths quite a bit. The amplitudes can be similar. They're transverse waves, just as a reminder. But the wavelength of the light is what determines the color you're seeing. You see the numbers on the bottom there? So purple is also the most high energy because it's the higher wavelength. Red is the lowest energy as the longest wavelength. And those are in nanometers. So the length of the waves of color you're seeing are measured in nanometers. Now visualize those meter sticks that I have in my classroom. A nanometer is 1 billionth. You have to chop that up into 1 billion pieces to get to 1 nanometer. So the wavelengths of light are very, very small. Okay. Now, you notice that white light wasn't on there, right? Oop, see, there's no white light on there. What actually makes up white light is all of these different colors. White light is actually every color combined into one. And you can split light using a prism, and we will do more on that soon. I really like this GIF in particular too, because if you notice when the waves are coming out, you can see that the purple has the smallest wavelength and red has the bigger wavelength. So that's pretty neat too. Again, white light is not only white, but it contains all colors of light. And just like in art, there are primary colors, right? Red, blue, and yellow. You mix those together to get any of the colors you want. The same thing is in light, but actually they're different colors. The 3 primary colors of light are red, blue, and green. You mix them together, you can get all these different colors. Red plus blue equals magenta. Green plus red equals yellow, green plus blue equals cyan, and then all 3 of those together equals white. If you are in the musical, or have been in the past, or if you've been to any stage shows, you'll notice that actually the lights up on the stage are not white typically. You'll have spotlights and stuff like that, but to light the whole stage, they're typically not white. They are red, green, and blue. I know this one is really hard to digest, but look up some videos online of color mixing with light. It's pretty cool. Now, how do we see color? So we've already addressed that light hits an object and reflects into our eyes. But if it was all white light and it would reflect all the light, we would just see white all the time, which we don't, right? We do see white, but I'm seeing plenty of other colors right now. So white light hits an object, then all colors except the one we see are absorbed. So if I have, right now I'm wearing orange, so light hits my shirt, it absorbs everything except the colors that mix to create orange, and then bounces off that, and that's what we see. So you can kind of see in this diagram here, white light comes in, it's got the green, red, and blue to a red object. Green and blue are absorbed, and red reflects. So that kind of makes sense, right? That's the color that's leaving the object. That's the color that you receive in your eyes. So that's how you're able to see it. That kind of makes sense. White light on a white object will reflect all of it. White light hitting a black object will reflect none of it, which also makes sense if you think back to, I don't know when you would have done this, but black is very absorbent, right? You don't want to wear a black shirt out in the sun. And that's one of the reasons why it absorbs all of that light. It doesn't really reflect light in general. This is also kind of the reason why different things look different in different lighting. Okay, so something, if you take an object outside, you're going to see basically the true colors of that object. But sometimes when you're inside, it doesn't necessarily look exactly the same. It might have a little bit of a different tone to it. And that's because lights and light bulbs and everything doesn't always put off the full visible spectrum. Actually, I know in my classroom, they're a little bit orange tinted. So they're actually losing a little bit of that blue range. And if that light isn't coming in, you can't see that light, right? It can't reflect light that's not there. So we will be exploring that a little bit more. With seeing what happens with different objects and light filters. So might be a little bit confusing for now, but hopefully that will get clarified. Light filters are a really awesome and easy way to see the difference and really what we're talking about. If that light doesn't come in, you can't reflect that light to see that color. So it often will come up as black or something a little bit off from the color that you were expecting or that you would see in full white light. All right, everyone. That's all for today. Have a good one.